Thank you, Greg, for the introduction, and thank you, everyone, for staying so late in the conference and attending this talk. So although the directed Steiner network is in the title, mainly today I will focus on the 2CSP and the hardness of 2CSP that we can achieve here. All right, I guess I will not use this. Oh, sorry. All right, so let's recall what is the 2CSP problem. So in the 2CSP problem, the input instance is a 2CSP instance, which consists of first a constraint graph. So this is just an undirected graph where the vertices are the variables of our constraint satisfaction problems. And there's an edge between two vertices if there's a constraint between them. And this is called the constraint graph. And the second part of the input is the alphabet set or the domain. So these are the values that we can assign to each of the variables. And lastly, we have the constraints, so one constraint per each edge. So this specifies the possible assignments to the two endpoints that we consider to be to satisfy this constraint. And the goal of this problem is to find a labeling or an assignment that satisfies as many constraints as possible. And I will use the word value to refer to the fraction of the constraints that can be satisfied by the best possible labeling or assignment. And many of the known optimization problems can be phrased as 2CSP. For example, max cut is just a 2CSP where the constraint graph is the input graph, and the alphabet set has size only 2, just saying which side of the cut the vertex is on. Unique games are also a special case of 2CSP. So unique games is just a special case where the constraints are the constraint of unique type or one-to-one constraint, where if we assign a value on one end, then it fixes the value on the other end. So let's see what do we know about approximability or inapproximability of 2CSP. So for example, in the max cut case, we know the 0.878 approximation algorithm, and we know that this algorithm is basically tight in that getting anything beyond this is unique games hard. And in fact, this is roughly true for all CSP with constant alphabets. So we know that for constant alphabet CSP, the basic SDP actually give us basically the best possible approximation ratio. But now things get a little more interesting when we allow the alphabet size to grow larger, and in particular to be dependent on V or to be much larger than V. And in this landscape, so let's take a look at what do we know in this landscape. And from here on, I will use a big N to denote the product between the number of variables and the alphabet size. So since the early day of the PCP theorem, there is a conjecture of Belair et al., which says that the 2CSP is hard to approximate to polynomial ratio in N. So this is N to the B for some constant B greater than 0. Unfortunately, although it has been open for more than 20 years, it still remains open until today. And this is a special case of the so-called sliding scale conjecture. Now, if we want NP hardness, the best known hardness of approximation now is only a polylogarithmic in N. So it's log N to the C for every constant C. But if we allow the assumption to be stronger and stronger, then we actually get a better and better hardness. For instance, if we assume that NP can be solved in quasi-poly time, then the ratio can be improved to 2 to the log N to the 1 minus delta. And if we assume ETH, which I will define a little more formally in a couple of slides, then the ratio can be improved to N to the 1 over poly log N. So I hope I get the number of logs correctly. And lastly, we assume even stronger that the gap ETH hypothesis, then the ratio can be improved to N to the any function that goes to 0 with N, so say N to the 1 over log star N. So we are super, super close to getting polynomial ratio N to the B for some B, but we're not quite there yet. So here's a question. We can get a ratio that is polynomial in both sigma and V. How about we separate sigma and V and try to study them separately? So it turns out that in the case of sigma, it has been known for a long time that 2CSP is hard to approximate to polynomial factor of sigma. However, for V, there's no known hardness result of the form that is polynomial in V before at all. And this leads us to our result. So our results show that if we assume the exponential time hypothesis, or ETH, then 2CSP is hard to approximate to V to the 1 minus little o 1 factor. So this is not only polynomial, but almost linear factor. And if we assume gap ETH, which is stronger than ETH, then we can rule out not only polynomial time algorithm, but parameterized algorithm where the parameter is the number of variables. So this is indeed what Greg said earlier. This is the regime where the alphabet size is much, much larger than the number of variables. And the running time of the algorithm is allowed to depend to be any function of the number of variables, but only polynomially in the size. So poly n and fv, where f is any function. And this, I will sometimes refer to this as FPT time. And let me note here that these ratios are almost optimum in the sense that there is actually a trivial algorithm that can yield a V approximation ratio. So up to the little o 1 in the exponent, this is optimum. So before I get into the proof, let me state the hypothesis a little bit more formally. So the exponential time hypothesis, or ETH, states that there's no sub-exponential time algorithm that can solve 3SAT. And the gap ETH hypothesis is a strengthening of ETH, where it says that not only that we cannot solve the exact version of TSAT, but we can even solve the approximate version of TSAT, where we want to distinguish the case where the formula is satisfiable and the case where it's not even 99% satisfiable. And our two hardness of approximation results actually use the same reduction, but with different parameter initialization. So let me focus on the gap ETH hardness result. So what we want to prove is we want to show that if gap ETH is true, then there's no FPT time algorithm that can distinguish between 2CSP that is fully satisfiable and one that has value roughly 1 over k. So what kind of reduction do we need in order to prove something like this? So recall again that this is our starting assumption. This is the gap ETH assumption. We have a low bound that is exponential. So now our reduction doesn't have to run in polynomial time anymore. In fact, it can run in almost exponential time. In particular, our reduction, we have two parameters, k and r. And here, k you can think of as some large constant independent of n, and r as something that grows with k, but grows very, very slowly, something like log k or log star k. And the reduction will produce a 2CSP instance that has k variables, so small number of variables. But the alphabet size sigma will be quite large. It will be exponential in n over r. And in the yes case, indeed, the 2CSP will be satisfiable. In the no case, the value will be small, and we will get our result. And in particular, since the size now is exponential in n over r, the running time low bound that we get is big N to the r, which is now big N to the something like log k, something that grows with k. So indeed, we rule out polynomial time algorithms. OK, so the reduction is proof is very simple. So hopefully, I can tell you a little bit about it in the remaining time. So let's say we start with a 3SAT formula with m clauses. And we can assume with a lot of generality that m is linear in n. So we will construct our 2CSP instance as follows. First, we will pick k random subset of clauses, each of size m over r. And these will be our variables. So we have k variables indeed. And the constraint graph is just a complete graph. So there is a constraint between every two variables here. And what would our alphabet size be? So the alphabet set would just be the partial assignments that satisfy each vertex. So for instance, for T1 right here, it contains only one clause. So now the alphabet size will have size 7. And each of the 7 elements will be associated with all the 7 assignments to these 3 variables that satisfy the clause. And the constraint is also defined very naturally. So we say that the 2 partial assignments satisfy the constraint if they agree. And by agree, we just mean that they do not contradict on any variable at all. So for instance, the assignment that assigns 0 to every variable in T1 and the one that assigns 0 to every variable in T2 would assign the constraint C12 on the other hand, the assignment that assigned all 1 to T1 and all 0 to T2 wouldn't satisfy C12 because they contradict on X3, for example, in this case. So this is the whole reduction, so extremely simple and extremely natural. And let's see let's see the property of the reduction. So first, the number of variables is indeed k, and the alphabet set size is indeed exponential in n over r because each subset has size only m over r, and so the number of partial assignment is at most 2 to the 3 m over r. So in terms of size, we are in good shape. How about in the yes case? In the yes case, if we have a satisfying assignment to the 3-stat formula, then it's very simple to pick a the labeling for our CSP. In particular, we can just look at one satisfying assignment for the 3-stat and just pick all of its restriction to each Ti. So we will indeed satisfy all the constraints of our 2 CSP. So we are in good shape. Now, there's only one thing we have to prove. We have left to prove, which is the no case. So we want to show that if the 3CNF formula is not 99% satisfiable, then the 2 CSP instant has very, very small value. So let's try to prove the contrapositive here. But what does it mean to actually prove the contrapositive here? So it means that if we have a labeling of our 2 CSP instance that satisfy at least k to the little 1 over k fraction of the constraint, we want to somehow get back an assignment to our 3-stat formula that satisfy at least 99% of the clauses. So for the purpose of this talk, we will prove something a little bit weaker, which is that if the labeling satisfy roughly 1 over root k fraction of the constraints, then we will get back the assignment for our 3-stat formula. So what does it mean for us to have a labeling here? So a labeling in this case is just a bunch of partial assignments to T1, so on, and to Tk. And let me join a pair of assignments by an edge if they agree. So these are indeed the edges, the constraints that are satisfied by this labeling. So since we assume that this labeling satisfies at least 1 over root k fraction of the constraints, we know that the number of edges is at least something like k times root k. So you don't have to worry about this thing too much now. But, and this graph, I will call it a constraint graph. So let's do the following thought experiment. Let's suppose that somehow our graph has a clique of a pretty large size, let's say 1,000 times r size clique. I mean, in general, we will not have this, but this will be a good starting point in getting to the actual argument. So suppose that we have a clique of size 1,000 times r. What does it mean? This means that we have 1,000 times r partial assignments that all agree with each other. So this means that we can find a global assignment that agrees with all of them. So this global assignment will satisfy all the clauses that appear in at least one of the sets. But recall that these sets are random subsets with 1 over r fraction of the clauses. So it means that the union of them will very likely contain 99% of the clauses. So indeed, in this we are done here because this global assignment satisfies at least 99% of the clauses. So good. So just a one-line recap here. We just said that it suffices if we can find 1,000 times r partial assignments such that all of them agree with each other. And it's not hard to see that we don't really need this. We can relax this a bit and ask for a partial assignment that only approximately agree with each other. And by that, I mean they agree on 99.9% of their intersection. And further, we can even relax this further and ask for partial assignment such that 99.9% of the pairs approximately agree with each other, and it's also not hard to see that this still suffices. So since we are now talking about approximate agreement, let's revise our consistency graph so that we can talk about approximate agreement here. So let's take a look at what I would call the 2-level consistency graph. So this is a graph where there are 2 types of edges, blue edges and red edges. So the blue edges are the edges as before. So these are edges that are satisfied by the constraint. These are the total agreement edges. But we will also additionally have red edges. These are the edges such that the 2 endpoints strongly disagree in the sense that they do not even approximately agree. And now our task here can be rephrased as follows. We want to find a subgraph of large size so that only at most 0.1% of the pairs are the red edges, because these red edges are the pairs that do not even approximately agree. Okay, so we will try to do this, and to do this, we have to exploit some sort of structure of this two-level consistency graph, and this structure I will call it red-blue almost transitivity. So it says the following: if you have a red edge with two endpoints t and t prime, then they can share only a few number of common blue neighbors. And you don't have to worry about the exact number of neighbors. It's not that important, but just notice that it is much, much less than k. And why is this the case? This is the case because if t and t prime has a common neighbor, say t1, then it actually means that the two assignments must agree on t1. So if it has, say, neighbor t1 to tq, then the assignments must agree on t1 union t2 and so on to tq. So and also recall again that these t's are just random subsets. So if q is too large, then this union will contain almost everything. But this would contradict to the fact that there is a red edge between t and t prime, because that means that they disagree on many of the vertices. So indeed, we have proved the red-blue transitivity of this graph. Okay, so let's see how we can use the, yeah.
So is this true deterministically or with hypothesis?
Yeah, so actually this is true deterministically, and you can even deterministically construct the set with this kind of property. Like it's just a disperser basically. Yeah. So okay, so let's now see how we can use this red-blue transitivity to get what we want. So recall again that we have two-level consistency graph. We want to find a subgraph such that very few of the pairs are red edges. And we just show the red-blue transitivity. We say that every the two endpoints of any red edge can share very few number of blue common neighbors. And let me also assume for simplicity that the blue graph is regular here. And so the degree of the blue graph here is something like roughly root k. Okay, so here's how we prove this. Extremely simple. So we look at the number of, let's count the number of all red, blue, blue triangle. So this is a triangle with one red edge and two blue edges. So from our red-blue transitivity, we can actually bound this to be at most k squared times some small number. This is because the red-blue transitivity exactly says that if you fix u and v, then there is only very few choices for v. And there's only k squared choices for u and v. So this is the bound that we get. So there are k choices for the v. So there must be some fixing v star such that if we fix this, then the number of red, blue, blue triangles such that v equals to v star is only something like roughly k. Now, this is the subgraph that we will take. The subgraph that we take is just the blue neighborhood of v star. Why does this work? This works because the bound on the number of red, blue, blue triangle exactly correspond to the bound on the number of red edges in this neighborhood. So we know that the number of red edges in this neighborhood is really small. It's something like only k. So if this neighborhood has size something like much more than root k, then we are done because only about at most 0.1 fraction will be red edges. So this is basically the whole proof. So very simple, right? And yes, so I mean, I almost didn't hide anything except the fact that I made a little bit of a stronger assumption that d is at least root k instead of d that is something like k to the little of 1, because this root k would only give us root v hardness of approximation instead of v. But this whole thing is basically give you the root v approximation. I didn't hide anything at all. So let me say just a couple of words on how to get from the root v to v. So in the root v case, we consider this red, blue, blue triangle. So to get from root to break this barrier, we just consider the most natural generalization of it, which we call a red field L walks. So this is just L walk of blue, like length L blue walks, such that all the non-consecutive pairs are joined by red edges. And indeed, if we count this instead of red, blue, blue triangle, then we get our whole proof. OK, so let me conclude here. So in this work, we show that 2CSP is hard to approximate to almost linear factor in the number of variables. And in fact, in our soundness proof, we prove something that is a little bit more general than anything about 2CSP or 3SAT. In particular, what we show is that if we are given a bunch of functions whose domains are random sets that are pretty large, and these functions locally they agree, then we can actually find a global function that approximately agree with many of these functions. And this kind of local agreement to global agreement is sometimes called an agreement testing theorem or an agreement theorem. And as a corollary of our result, we also get a k to the 1/4 hardness approximation for directed Steiner network. So this is the directed version of the Steiner forest, for those of you who came for the Steiner forest talk a couple of days ago. And the base approximation ratio here is roughly square root k. And so our result is the first polynomial in k hardness of approximation result. And few open questions. So of course, the sliding scale conjecture is still open. So please try to prove or disprove them. And another question that I think is perhaps, I think is very tractable is trying to close the gap from in the directed Steiner network from trying to push the 1/4 to 1/2. And sort of the reason that we get this 1/4, there is one step in our proof that lead us to loss of square factor where we go from the maximization version of 2CSP, which is what we have talked about today, to the minimization version. And in this step, it seems like the square root loss is not necessary, but we just don't have the tools to analyze the minimization version yet. So if it's totally possible that you can, that there is some sort of arguments that can give a tight argument, a tight ratio there, which would also give a tight result for directed Steiner network. And that's it for my talk. Thank you very much. No, not yet. I mean, another open question, like, can you prove poly in K hardness for densest K subgraph?
No, but like to almost to get like constant factor, like get a.
No, yeah. I mean, we really need to use the fact that like each of the assignment that we select, that we select at most one assignment from each set. If we are allowed to select multiple assignments from each set, then yeah, we have the same problem as we always have.
So I was going to ask, are there any other candidate problems which you could look to get in approximately?
Yeah, so I think like densest K subgraph is one of them. It's totally possible that poly in K is provable via some sort of this technique, but there is certain barrier there that we have to overcome.